Hello everyone. So in this session we are going to discuss something related to industry perspective on compiler, and speaker for this session is Sushim Shrivastava. So he's working in Qualcomm from past 17 years, and he worked in different roles contributing to wireless systems development, and more recently he's working on compiler, cloud, machine learning, and software security. So apart from that, he's a very good person, and even in future, if you want to contact anything or you want to discuss anything related to compiler or any use case in industry, then I need permission from Susim, but I think he'll be very happy to contact with each and everyone. So now stage is yours, Susim.
Thanks a lot, Avnish, for a more than nice introduction. So, I will, as Avnish said, for any career opportunities or how, in systems domain, career spans or how it evolves, you can contact me. I'll be more than happy to help if I could be of any help. With much ado, we'll jump into this session. And this session is not exactly academic in nature. I am trying to connect what you study and how it is getting implemented in industry, and why more and more, like, systems engineers are required. So I'm only taking the from systems engineering compiler perspective, that why compiler teams are growing in every company, doubling every couple of years, and why more and more compiler work is coming. And I'm going to show you some use cases how compiler is helping, you can say, other domain experts like ML, image processing, and why this awesome camera on a smartphone is not possible without effort from the compiler engineering team. So I'll just try to connect between the theoretical aspects which we are studying in our class to how they are enabling the products in real industry. So first, I will try to set context. Since I am from mobile phone or smartphone background, I will take references or use case from smartphone background, but they are equally applicable in other backgrounds too. So if you see, the mobile smartphones are an amazing technical achievement. So this is, I'm not talking about this slide from the perspective what achievement mobile phone is. I'm trying to explain you complexity what mobile phone has, or mobile evolution has brought about. So there is mind blowing performance. So right now, if you look at CPU scores, they are better than supercomputers of 1990s. Multimedia, I still remember, SIF resolution multimedia on earlier phones, and now you can get 8K Ultra HD video player recorder on mobile phone. Navigation is, of course, a use case which you use, and the broadband speeds, we are looking at 7.5 Gbps. We recently tested in one of the operators in North America. Internet connectivity everywhere, and long battery life. This is an extremely important point which compiler engineers are bringing, enabling it. So a 15 watt, a 60 watt bulb running at your house for 15 minutes, that is the amount of energy a mobile phone consumes during 24 hours. Again, this slide is just setting the context. We'll get to the next one. I hope most of you have same area every 2.0 more than the law. It was an observation which held true for very long time, but Moore's law is slowing down a little bit. We'll come to that point a little later. So now we look at the comparison between two smartphone devices. The left one on 500 nanometer process in 1995 with 1.4 million transistors. Now, if you look at 7 nanometer process, now we have 5 nanometer recently. This is slide is slightly older. 10 billion transistors, so 10 billion logical units on a chipset. 7.5 Gbps 5G modem, 2.84 gigahertz octa-core CPU. Look at, 4 rear, 1 front camera, 8K video encode decode, Xbox One class GPU, and so the smartphone has gone really complex. So what has happened in this complexity? What it brought about? So it's a very simple thing. Now in a mobile phone, there is a CPU, there is a DSP for modem, there are smaller microcontroller units, there are custom DSPs for compute, custom DSPs for audio. So there are a hardware accelerators. So there are different CPU architectures which exist within as small as compute devices, a smartphone. So because of these all advanced feature enablement and all those advanced technologies brought to smartphone or other compute devices, there has been a lot of custom accelerators, custom hardwares, different computer architectures, different underlying architectures have come into the picture, which run on different instruction sets. So first two slides, you can take a message that computer architecture has been evolving very fast, and there are different kind of computer architecture with different instruction sets which are available, which a programmer needs to program. So this is the summary of first two slides which you need to take away. So what challenges are coming up? So Moore's law is slowing down. We are not expecting hardware to be improving as fast as it was, doing it earlier. Earlier, there was one common thing like the hardware will improve or faster than the software. Software will catch up later. Like a new hardware or new architecture will come in. The first problem used to come was people will say this new hardware is not easier to program. Software will catch up in a while to exploit all capabilities of hardware. I remember a use case from one of the DSPs where the special hardware block was put in the DSP to accelerate a particular scenario, and it got utilized 4 to 5 years later because software caught up using that particular block 4 to 5 years later. Now, as I showed in earlier slides, there are plenty of hardware blocks are augmenting the main CPU, which have again different instruction sets. There are a lot of hardware accelerators for very specific tasks like image processing, ML applications. These different hardware accelerators have this explosion of different hardware accelerators has made developers' job difficult. I'll tell you why. Suppose you are an image processing engineer or a machine learning engineer, and you need to write a code which should be efficient, because you would have been heard in multiple news forums, even on the not handheld devices. Earlier, when I started my career, we were worried about power consumption only on handheld devices because it had a battery. The computers which are connected to power, we were not worried about power consumption because there was no portability. Power connection is there. But now we are worried about power consumption even in higher end CPUs, because you would have been heard about heating up of servers. The servers or those cloud servers, all those companies are worried about they're heating up too much. So you need to do more per milliwatt, more per cycle. So that's one part. The other part, so you need to write an optimized code for underlying architecture. Now, image processing or machine learning, the two examples which I'm taking right now, those two domains itself are very complex. So expecting an engineer to understand the domain like image processing or machine learning and also understand underlying architecture and write an optimized code for underlying architecture is probably a very high expectation. Also, not only one underlying architecture, there will be different underlying architecture. Even the same architecture might have different versions. Like, for example, Qualcomm Hexagon DSP from version 60 to 75, there might be a new instruction which might have been come in. So now using that instruction or the vector size has changed. So you need to go back and change your code again. So an engineer, image processing and machine learning engineer, to keep up with the architecture changes or coding it for optimize for different architectures, it brings in a lot of challenge. Now, one more thing is like earlier computing meant for us a computer which was a supercomputer or a x86 or a laptop or a desktop. But now computer is an IoT device which is kept in Siberia, where we can go and replace battery once in 10 years. It needs to wake up absolutely when it is required to wake up. it should not constantly function, and it has a very very small CPU running in kilohertz or megahertz. And then there are supercomputers also. So there is, like, in case of IoT, you need to use a very small CPU with very lesser memory and a battery which need to be last very long time, a small battery. So your code has to be optimized for underlying architecture. You cannot have an unoptimized code running on underlying architecture. Obviously, security is a major concern in all the connected world. So it is not exactly the compiler, it is a little bit of program analysis domain, or we can say informal methods, or in broadly it will fall. So but the recent most popular compiler, LLVM, has static analysis tool which helps you solve a lot of security issues. So we'll cover these use cases, and let's see, going forward. Bottom line, we cannot count on only on improvements in hardware for solving problems and technological progress. Software has to contribute, where compiler has to play a major role. So while we move further, I'll bring in one more point. So software engineering has there for a while, and there is a lot of legacy code which exists. So any new project you do, you will be using libraries or the legacy code from previous projects. You will not rewrite, you will not reinvent the wheel, and you will only write the novel part, what you are doing. Now, 80-85% code in a project is legacy, which was written for an underlying architecture which was 4-5 years old, 8-10 years old. So that code is not optimized for your current architecture on which you will be porting it or using it. There also compilers come a lot in picture to help. We'll see that going forward. So compilers abstract those hardware complexity. Now, how compiler comes in picture? Let's say image processing engineers need to care about only image processing part, and rest compiler can take care. It helps in reducing the code size and great performances. And also, when the majority of production code, 80-85% of the code has remained untouched, we can bring in those compiler optimizations so that the code generated now from that legacy code is efficient on that underlying hardware architecture where it is going to run. With the compiler's code becomes portable, easy to test, debug, and profile. I'll again go past this slide a little faster so that we can see the example. So solution is like domain specific languages. Like C++ and Java are a little more complex than domain specific languages. Also, DSLs can be used by non-programmers who are expert in a particular domain. Why I'm using word non-programmer here? See, you need not be expert in C++ or C and writing a code optimized for underlying architecture, but you may be expert in image processing and what you need to do to for that image to be a little better, to create the bokeh or a blur or anything like that. So you know the mathematical algorithms about it, but you are not so good at these low-level programming languages. So DSLs are way to go. So we will take the first example as image processing. So Halide is a new domain-specific language for image processing and computational photography. So what happens here is traditional languages were making parallelism, tiling, and other optimizations very, very difficult. So Halide what came in the picture, and Halide enables rapid authoring and evaluation of optimized pipelines by separating algorithms from computational organization of different stages of pipeline, the schedule. Programmer defines both algorithm and schedule, and front end is embedded in C++ for Halide. So even if your legacy codes exist in C++, you can write a new piece of code in Halide and embed it within the C++. So I'll just get into the slide where I explain you what algorithm and schedule is. So we are talking about horizontal blur in this example. So when you are processing a pixel, there are two things you are doing. You are doing a certain operation on that pixel, and other thing you are doing is how you are accessing that pixel. So that certain operation, in this case, the code shown on this slide is horizontal blur. You are averaging 3 horizontal pixels, the value of 3 horizontal pixels, and this is what your algorithm is. And so once you've decided your algorithm, you need not change your algorithm. The second part is how do you access that particular pixel for operating on it. So this is the one which will set the performance of your program, not the schedule, or no, not the algorithm. So schedule is what which fixes your performance of your program. Since schedule and algorithm are separated, once algorithm is perfected and bug free and all, you need not touch it. For performance, you just need to touch the schedule, and both pieces of code are very, very independent. You can see this slide, right? The animation, everyone. The animation is
Yes.
visible.
Yes, sir.
Yeah. So in typical image processing pipeline, there is a producer and there is a consumer. So here, if you see, these yellow are writes and blue are reads. So what is problem in this particular image processing pipeline? Can anyone tell me what's wrong here or why it is not optimized?
Sir, if we can optimize the writing process only because it's taking 2 by 2 cells and printing the average of them, I guess so, in the consumer part.
Uh, Another thing is okay. That's the next step. You're talking about algorithm. Do you see? We are producing the producer first, then we are reading the producer, right? The whole producer is produced first, and then we are reading. So the initial write what we have done, by the end, what will happen is it will be evicted out of cache. So when consumer starts consuming, it will have to fetch again from the memory, and it will make process slower. So it is a bad cache locality, which is obvious. Poor cache locality. Okay. So now let's see the next part. So what we can do is what we are doing here. I'm just taking you through some image processing concepts so that you are able to appreciate the later slides or the later presentation. So here we have tiled the producer in 4 parts. We are producing one tile and then consuming it, processing it. Then we do the second part, then consume it, third and fourth. So it helps us, like, the most of the data remains in cache, so we can process it faster. So consumer consumes it faster. So this is a tiling, which is a very common operation in image processing. So better cache utilization. Now with the modern DSPs, what has happened is we can parallelize things and we can process multiple pixels or a vector at once for better improvement. So if you look at this, there are parallelization between 4 threads, and we are processing a set of pixels at the same time. So tiling, vectorization, and parallelization gives you the speed. Now let's look at this piece of code in C++. So halide and C++, if you see the algorithm right now here for horizontal blur, pretty comparable. If we do this, if you look at the schedule on left side, you see we did the tile and unroll. If you see the code in halide on the left side is very simple, very minimal. You need not understand or be a C++ expert to write that tiling or unroll. You need to decide what is a tile size, what factor you want to unroll the loop, and boom, done. But in case of C++, you will have to write a pretty complex piece of code. And this, we are talking about a very, very simple algorithm, which is horizontal blur. Now, if we want to vectorize, where we are seeing, we are like in the earlier animation, we are processing a large number of pixels at once. In C++, it is not possible without auto vectorizer, where in Halide, there is a dot vectorize directive. You just call it with the vector size, and that is done. Now, there will be an obvious question in all of your minds, like, this code is very abstracted of Halide. How can it perform as comparable as to a handwritten assembly? We'll come to that part. We'll give you a real case what we have done. So this is a summary about Halide. The separation between algorithm and schedule is the key. So there was this second point which I'm writing, tuning and experimenting with computational organization to achieve high performance. So what happens is, as I said, like handwritten assembly code might be initially more optimized, but you cannot retry multiple iterations with different parameters as fast as you can do in Halide. So we had a real incident. We were on a initial days of Halide, we were on a road trip, and we were at a big gathering where we were showing why Halide is the way to go for image processing on DSPs. And then there was question by a very, very senior person who said, you are time and again talking about in Halide you can author very fast, in Halide you can author very fast, and you can optimize very fast, you can iterate very fast. Can you show us an example? So we, right there, they had their handwritten algorithm for box blur, which was giving performance around 4 or 5 milliseconds. I'm not remembering the exact number. And they said, can you write a box blur right here and prove your point? We said, okay, if you are willing to wait for some time, we can do that. So we wrote our box blur right there in few minutes. And then we ran for the first time. We got 30 milliseconds, which was very bad performance compared to 5 milliseconds. But within 20-25 minutes, we could iterate. We are constantly iterating and number is not changing much. But all of a sudden, with one iteration, it came around 10 milliseconds. We optimized a little bit more. And within 20-25 minutes, we could get to a 6.5 minutes of performance, 6.5 milliseconds of performance, which they would have been taken in a handwritten assembly very, very long time. So you can try quite fast, and your optimization of this all unrolled, tile, vectorize is done by the compiler team in the background. So compiler team comes into the picture, which makes sure that it runs optimized on the underlying architecture. So generation of highly optimized code for the architecture, the compiler team takes care of it. So this is an example. If you look at performance here, 3x3 convolution. So right side HVX intrinsics of hexagon DSP is written by the people who designed those DSP. So they knew architecture in and out. And 0.114 cycles per pixel is its performance. And the left side is written in Halide and generated code with the help of compiler, which is written by our compiler team. And it takes a lesser cycles per pixel. And you can very well see on the right hand side code is definitely not maintainable. If a new instruction comes in, or there is you need to change parameters to improve the, you want to try out different parameters and measure the performance, the iteration is not fast, the code is not portable, the code is not maintainable. So Halide, 14 lines of code, very concise, easy to maintain. Developers can quickly restructure schedule to optimize the algorithm. And whereas on the HVX side, it is, I think, 130 plus lines of code, because 94 lines are not shown here. So this is the first example. So advantages of using halide versus intrinsics or assembly. Developmental time and cost. Significantly more time is needed to author assembly and intrinsics compared to halide program. Assembly and intrinsics program, the person has to, or engineer has to understand underlying architecture perfectly, which is like very few people can be expert in both architecture and the domain. Also, then how many architectures they will learn. So this will limit the number of programmers which are available. Uh, so halide will allow programmer to focus on the algorithm and not on processor details. Of course, halide programs are scalable. You can write a very large programs. It is same C++ kind of structure, but intrinsics or assembly programming is not scalable for very large programs. There are automatic optimizations possible. Portability with halide, no change in code required for new versions of Hexagon or the DSP or underlying architecture. Compiler will automatically take advantage of new hardware features and instruction set. So while it looks like I was talking about halide for all the time, but underlying message here is that if there is a domain specific language, the domain expert can take care of the domain, and rest all can be left to the systems engineer who are writing underlying compiler. So at this point, I will take one more, a little bit of detour, or I'll say a little more explanation about. So compiler engineer is not just compiler engineer. By just knowing compiler design, you cannot be compiler engineer, a good compiler engineer, or by just knowing uh, compiler optimizations. Because when you write optimizations, when you have to generate code for optimize for underlying architecture, then you need to be having a decent knowledge of computer architecture. While having a, you know, while knowing a good computer architecture is required, then also brings in the advanced OS concepts while you are optimizing. And problem solving is, of course, is always uh, you know required for. So to be a good compiler engineer, you need to be good in compiler design. You need to have decent knowledge of high performance computer architecture, advanced OS, and formal methods. And while when you know this, you can do, I like, for a lot of people in industry who are themselves good programmers, they were such a big naysayer for domain specific languages, and to them this seems like magic. So yeah, so first example we took of halide, which is an image processing domain specific language, and image processing being enabled by compiler engineers so that uh, those HDR pipelines and camera pipelines can be written in halide without being worried about what architecture it is going to run on. The halide became famous with Google Pixel 1, the Google Pixel 1 ad, the best camera ever, which played on all the radios and everywhere at that particular point in time. So the whole, most of the part of that camera pipeline and all those pipelines were written on halide for that. And yeah, also another example which I'll bring in here, which was again from the real world. There are material engineers in Germany who were trying to write some code, image processing code, on our Hexagon DSP, that it should be able to differentiate between wood, rubber, plastic, and different materials. That use case was there. And they were material engineers, they were not software engineers. They could use halide and write that program, and compiler provided by us could generate optimized code for underlying Hexagon DSP. So this is another example from the real world where halide has helped non-programmers as such. but they were expert of their domain, which was material engineering. So while we just talked about halide, I will take you through another example. This example is again going to be not very different, just that reinforcing my case where TVM is a compiler framework for machine learning. So it is an end-to-end compiler stack, and there is a wide industry adoption. Amazon, Huawei, Intel, ARM, Alibaba, Nvidia, Facebook. A lot of people are using TVM. So TVM, we have added support for Qualcomm hexagon vector extension HVX to TVM, which already existed. The framework already existed. Now this is optimized for Qualcomm hexagon DSP. Again here, engineers will be writing code in Python, not Python-like, in Python with some additional directives like those unroll, tile, and all those things. And they will not be worried about the underlying architecture. So it has a Python interface, which makes it very portable. Like Qualcomm new hexagon DSP hardware features comes in, or you want to port it to altogether a different DSP, and that DSP architecture team or that hardware architecture compiler team has optimized the underlying compiler to generate code for that particular DSP or hardware accelerator or CPU to generate optimized code for it. The same code can be portable across family of DSPs and hardware. Same TVM code will exploit the new hexagon DSP hardware with updated compiler. The new hardware hexagon DSP version comes in, or same TVM code can be ported to different hardwares, just that the compiler team which is optimizing the or which is the compiler which is generating the code for that underlying architecture should be optimized for the underlying architecture with TVM. Again, it follows the same principle of separating algorithm and schedule differently. And we knew from the halide experience this works. So for TVM also it will work. Again, one very good point here, which I did not talk about halide. So suppose some of you who want to try out image processing, right? Try to write image processing code using halide or machine learning using TVM. So they both are supported in hexagon DSP simulator and hexagon DSP hardware. You need not have the real hardware to run your code, or to if you have an hypothesis like you've written an optimization, it will improve the performance. So you need not have a hardware to measure the performance and prove your hypothesis. So you can run on hexagon DSP simulator, and you can use TVM or halide both. Because that is one bigger problem I see when academia talks about that we want to do research, or we want to try to do something in other than x86, but we need a platform. So that was the reason we drove this simulator, so that if you need to run a program, you need not have an hexagon DSP hardware with you. You can run on simulator, because having an hexagon DSP hardware will again, if a new version comes in, then you need to procure a new version, and all those things will come in picture. But in case of simulator, you download the new SDK and you support for the new version. So focus for TVM is to provide ability to author ML ops and faster. Users want to run a wide variety of machine learning models, and diversity in models is expected to increase given the rapid changing ML research. There will be more and more models coming in. The complexity from here is going to get higher only. So now if we start again the same part here, I've taken the hexagon DSP as an example, but any underlying architecture, if we start hand authoring ML ops optimized for the underlying architecture in the intrinsic or assembly, it is very expensive. That ML engineer need to be expert in the ML part and rapid changing ML research. He or she needs to keep a pace with the rapid changing ML research, and he or she needs to keep pace with the rapidly changing the architecture and the micro architecture below. This cannot scale. This cannot scale. This is not possible to scale. TAVM will enable customers or engineers to author. Here, customers word is there because people buy our DSP and use it. So, sorry for that. To author ML ops and plug into Qualcomm's ML workflow. Customer do not or engineers do not need detailed knowledge of Hexagon DSP. They can author the code in high level Python and leave it to compiler engineers to optimize that code for underlying architecture. This will substantially increase the programmer base because they need to code in Python. They need not be worried about what is the underlying architecture. So the Python programmers are available much more than than Hexagon DSP or any specific DSP programmers. So this helps the programmer productivity. TVM also supports scalar non-HVX code generation. So if you have some part which is not going to run on DSP, TVM will also support the scalar part of the code. So you need not be worried about it. So programmers will author custom op using Python, and TVM will separate again into algorithm and schedule, exactly like Halide we discussed a little while back. Algorithm will define that computation. Schedule will transform an algorithm into to improve the efficiency. TVM compiler compiles Python up to Hexagon DSP. TVM generated op is then integrated into Qualcomm's machine learning workflow. User can run their ML model using generated custom op. So here another example. We don't yet have the performance number because TVM is relatively newer. So we are right now working on TVM a lot. Halide also. So if you look at quantized element addition, you look at the left side code of the TVM. That is a complete code. And on the right side, that is the hand authored assembly, is the code you see plus 562 more lines of assembly code not shown. So this definitely enables programmer base and the ML engineers to continue their research and work on their ML side of it rather than worrying about to write an optimized code for underlying architecture. So 25 lines of Python versus 601 lines of assembly. That is a very simple example I can give you. You can it is definitely visible that which code will be more maintainable, which is easier to understand, easier to debug. So definitely domain specific languages are way to go here. In this case is TVM, and leave all the magic to compiler engineers. So now while we are done with two examples, there is, I can say very fairly that there are more and more different computer architectures are coming in, evolving. There are more and more different instruction sets. So there is a huge dependency on compiler engineers. That's why I said initially, that's why the compiler teams is growing in every company. The size of compiler, we started with 7. We are at 21 or more than 21, I think 23, 24 in last few years in India. And we are looking at doubling in less than a year from this number. So if you compare 7 to already, we are close to 3.5 times. And from here, we are looking to double. So we are looking at 7 times in 4-5 years, the team size growing because more and more custom hardwares are coming. So compiler team has more and more responsibility to generate optimized code for different custom hardwares and more optimizations to be done. We'll probably come back to question and answer, while the last example is remaining. Let me go through that example and then probably we'll come to Q&A. So LLVM has static analyzer built in. which is an open source tool, because there are a lot of static analysis paid tools were available, but in case of LLVM, it is built in. As a developer, what I like is I get an immediate feedback while I compile. In case of those commercial tools, it takes a while for them to generate report and all those things. Uh, well, more than that, let me come to why the LLVM security tools, these static analysis, sanitizer, and all those things are important. So earlier you catch the bug, lesser is the cost to fix. This is a very, very simple thing. I'll give you an example from Qualcomm bug bounty program. Suppose our device is launched and there is a security expert who finds a bug in our modem. So reward per bug is $15,000 if it is critical. Similarly, there is a different reward for different areas and different criticality in our Qualcomm bug bounty program. So let's analyze what does it cost if a security bug is detected after we have launched the product. Costing of fixing these bugs at development time, let's assume 10 hours, $55 per hour engineering cost, $550. Cost incurred when reported at production, bounty payments we have to do. Huge engineering effort in fixing that bug and propagation to all the devices which are already in the market in the hands of the users. But the biggest cost to which we cannot put a dollar value is reputation damage. I still remember like one of the chipset companies 6-7 years back, they put a test code and they accidentally released that software in mobile phones with the test code. And somehow accidentally it was figured out if you send that particular chipset phone an SMS with a particular string at the start, it recycles the phone. Imagine the loss of reputation. Like you don't require any expert hacking to just power cycle that phone, to power off that phone at any point in time. From any mobile, you can send an SMS and that phone will power cycle with a particular string. And the string was very simple. So there are reputation damages, and ultimately that chip sales was affected heavily after that particular thing. Even if they fixed it, it took a while for people to get faith on that particular chip. It was one of our competitors, but yeah. Let's take even the dollar cost of fixing these bugs in production. Let's assume there are 10x cost in production is $5,500. Like why I'm 10x? Development time is $550. Why it is 10x? Because you have to fix the bug, you have to propagate to all the devices, you have to figure out all those branches it has gone in. There's a huge machinery which will work on propagating those fixes to all the chipsets, all the devices which has gone out. Let's say average bounty per bug is $7,500. So static analysis, even if catches 20 bugs, the money saved will be, which it catches much more than 20 bugs, is like roughly $260,000 and plus the reputation cost. Somehow there is still the sensitivity around static analysis is not yet there because everyone is rushing to put their product faster into the market. There was a rocket series and its version 1 to 4 were launched. Before launch of version 5, they found, you can Google this, you'll find this story. They found that there was a static analysis bug which is there in the legacy code for a while. So they said, since we have launched 1 to 4 without fixing this bug, let's launch 5 also without fixing this bug. 8 seconds into the flight, that this time that particular path was hit and rocket went into flames. 8 seconds. 300 million worth dollar. I'm not considering cost of the development cost and all those things, the engineer salary and all, just the cost of the rocket, $300 million went into flames in 8 seconds for not fixing and static analysis bug. So at this point, like, the LLVM essay is an open source uh, tool. And many of you, if you would like to do a small project to a large project, there can be a lot of work can be done. You can add a simple checker in LLVM essay, upstream the code. See, your upstreaming the code is such a huge contribution to the community. If you write a LLVM checker, static analysis checker, and upstream the code, the whole world will use it. And they are looking towards LLVM static analysis because, for example, in the auto world, there is open source tool like our LLVM essay or any static analysis open source tool does not have as much coverage as they will expect for the auto standards. Very simple projects can be very easily written. Two very complex projects are available in LLVM security in the field of writing static analysis checkers or sanitizers. And you can do that. Summarizing this presentation, hardware diversification poses a lot of challenges. Difficult to port new cases to different accelerators. The new accelerator comes in, your legacy code becomes useless or maybe very unoptimized, even if it compiles and work on that one. So compilers will come to rescue here. Embedded systems have very, very specific constraints, low memory, performance power constraints. So you have to do more per milliwatt, more per cycle. Security is a major concern. We need efficient tools and techniques to overcome these challenges to keep up the pace of rapid technological advances. Like, so the tool chain or the compiler is very, very important in current day scenario. I hope these 3 examples were able to put some perspective into how industry is. If you look at now, you can connect it back. I talked about awesome camera enabled by Halide. In very soon you will see the TVM authored machine learning engines running on, or ops running on a lot of smartphones, compute devices, IoT devices, voice and music, automotive devices. So, and again, for target architecture, the optimized code will be generated using the compilers. I'll open here for Q&A. Even if you have a career related questions, because Avnish has volunteered me already, I'll answer those too. Like if you say you want to work in compiler design, what does it entails and what you need to do, or how is a career for a compiler engineer? Even I will answer those questions, as Avnish has already volunteered me for that. And I don't say no to Avnish.
Hello, sir.
Yeah, please go ahead.
So I have 2 questions. One about the talk that you gave, and one about the thing that you just said about this career in compilers. So I'll first go with the question about Halo, TVM actually. So you mentioned that it's the language being used is Python, right? And you are talking about really good performance. And so since we all know that like a Python is a relatively slower language, are we talking about a JIT-based compiler or something like that for the purpose of speeding things up?
We are not doing JIT yet, but I heard there are in community that people are trying it. Our is like compiled earlier in time, and the images are generated, and that's how they run on the handset. And we are able to generate very good performance as from the Halide experience. So this is like custom optimization done by our team, which will make sure on Hexagon DSP it runs optimally. So our work is not JIT based. Ravi, are you there on the call?
Yes, Sushim, yeah.
Yeah, no, I just want to make sure Ravi is more updated than me. Have we done anything JIT based, or we are like
No, to answer Rahul's questions, no, this is ahead of the time compilation,
yeah?
Rahul. So basically, we don't actually run the Python code directly on the device. So we cross compile it for Hexagon. Um, uh, Cross compile the Python code, Python op for Hexagon, and then run the generated Hexagon code on the device.
Right. Right. So I'm trying to understand the pipeline here. So is Python put through a source to source compiler first to convert it to something more faster, or is there a front end that explicitly, like, say, converts it to LLVMIR or something?
Right. Yeah. The TVM framework converts it to LLVMIR, and
Yeah.
So there is a specific Python front end that is being used, right?
There is no okay. So basically, there's no front end. I mean, technically, there is no front end as such for Python in TVM.
Yeah,
It's
exactly. That's exactly why I'm asking this question.
yeah. So basically, you compile the script with your Python interpreter itself, like the existing Python interpreter that you have, and basically you link it with the TVM libraries, and the libraries will take care of generating the code for Hexagon.
Right.
So as I said, it is the image generated ahead of the time.
Right. Oh, got it. Understood. So yeah, the next question is, you also mentioned about microarchitecture, like in context. You spoke about a few topics that a compiler engineer needs to know and all that. So how important would you say understanding of not a specific microarchitecture, but in general, microarchitectures? How useful is it, or how important is it for a person to know microarchitectures?
So I will say knowing principles of high performance computer architecture, let's say knowing all the principles or all the things listed in famous Hennessy Peterson or any high performance computer architecture course, that will be enough, because as and when you require any to work on any micro architecture, you'll be able to catch up faster. Understanding a particular micro architecture is or a particular hardware architecture probably is not required.
No, the reason I ask is because I've generally seen that. Okay, yeah, I mean your answer tracks, but my experience is that microarchitectures are generally shrugged off. Like only
Yeah.
when you come to a very specific problem where you need to like know about it, only then you think about, oh no, I had to know this beforehand or something like that. So would you suggest people to be generally more aware of microarchitectures, or is it acceptable to be just to come to a problem where we need to know that and then get to know about it?
You might get a conflicting opinion here, but first let's go with me, and then we'll have Ravi speak about it. In my view, once you start working on something, then learning about that particular micro architecture should be okay. Along your compiler work, it will not take much time. Ravi, you have a different opinion or something?
I agree to that. Yeah. So you don't need to know all the details about the microarchitecture. Once you have fair bit of understanding of the basics of general computer architecture, it should be good.
Yeah, right. Cool. Got it. Thanks.
Yeah, hi. I have a question. So, does Qualcomm extensively use LLVM in its compiler solutions, or do you maintain something of your own, like Intel's compiler, which is proprietary?
So we have both things. Like a small part of our code is proprietary, but majority of comes from the LLVM repository. We constantly keep rebasing it. The reason being, using from open source repository, like very small part in a single digit of percent of the overall code will be our proprietary, and rest of all come from the LLVM open source compiler. The reason why we keep a small thing proprietary is for competitive advantage. Let's say something we are working on academic optimization, which industry still thinks it is academic and they are not using it. So our compiler will perform better as compared to LLVM open source compiler available. So in Qualcomm, we generally are trying few of things which are still considered academic by rest of the world. We try it. If it works out and give us performance improvement, that particular competitive advantage we keep private. Rest all is we work on the open source repository.
All right, thank you. The reason I asked was even I am interning at a compiler team right now, AMD's AOCC. So just seeing how all the companies are moving towards LLVM and MLIR, it seems to me that proprietary compilers will soon be a thing of the past. Reason of this is because LLVM moves very, very fast, and it's hard for any team of like to keep up their own proprietary version that's on par with LLVM.
Definitely, like if you use the open source version, then whole world is testing for you. If you go private, just your testers are testing for it, right?
Yes.
So the collaboration works. So we are a strong believer in open source, but again, we have to maintain our competitive advantage also.
Yeah. Thank you.
Any other questions?
Yes, sir. I wanted to ask that. So in Qualcomm, so the code is written in Python, converted into LLVM format.
Yes.
So
For TVM, for like there are teams within a Qualcomm who write C code also, which compiles through our compiler. Here we took Halide and TVM example. The reason being to show what magic compilers can do.
okay. So like Halide is the mid process between the high level language and the LLVM.
Halide is the high level language, domain specific language for image processing. So
Okay.
where you can just call so image processing engineers actively are using Halide, because for their as I showed in the example here on this slide, this slide. So the previous slide, let me see this one. Yeah. So here, if you see C++ and Halide looks comparable when we are doing horizontal blur, average of 3 horizontal pixels. But in case of scheduling, for an image processing engineer, it is very easy to write f.tile and the tile size what he or she wants to do and unroll with a parameter he or she wants to unroll. But in case of C++, it will become really complicated. And if it is he or she has to vectorize it, this will not be available in C++ without an auto vectorizer. And with auto vectorizer also, it is not very simple. So Halide is a domain specific language for image processing.
So it's basically a language because
Yes.
I was currently reading about Swift. So they use an intermediate code named SIL, through which they pass the code, and after SIL goes through LLVM.
Yes.
So I thought that Halide must be also like similar.
No, Halide is a high level domain specific language for image processing.
Understood. Thank you, sir.
Yeah. Any further questions? Not only compilers, but yeah.
So
Career also. Yeah, go ahead.
So we talked about the difference between the Halide and the C++, but nowadays we have also like various pragmas like Xilinx. Like if we talk about Xilinx products, so the framework they provide, they usually provide some directives of pragmas which we can like put into our C++ code, which enables efficient like vectorization or tiling of the image processing task code. So in this picture, like where the scope of the highlight is, like because at the end, like the programmer has to learn a different language, and if a programmer is efficient in C++ language, he might be reluctant to learn a different language for simple image processing tasks. So, like,
Yeah, that's a very interesting part you have brought in. So that we face within our company also. There are people who are so expert in our architecture, and they are so expert in C++. They want to write a C++ code, right? But in case of, let's say, a image processing engineer who is conversant with C++, but in C or C++, when they are writing the code, they have to bring in the assembly element to optimize it, or the intrinsics elements for our underlying architecture or any underlying architecture. Rather than that, they can quickly learn. Halide is a very, very simple language here. As you said in Xilinx, as you said, they have their proprietary, which provides within C, C++, they can do tiling and all those. So they are also doing for the same reason, because learning the underlying architecture of programmer is tough. So they provide something, whatever you said, custom thing for doing tiling, unrolling, and all those things. Similarly, the halide also can be embedded in C++, and you can write your custom code, small piece of code in halide, which can be plugged in into C++. But writing in halide will absolve you, or will free you up from trying to understand that what how to tile, what is the instruction set, what is the HVX instruction set, intrinsic instruction set on an underlying architecture. So it frees you up from that worry. So same thing, what you are saying is you are justifying the case for halide, because in case of Xilinx also, what you are explaining is they have something custom which helps you to tile, unroll, and all those things easily. Same thing halide is doing. So whether you learn the halide directives or you do another custom one, the whole case I'm trying to make here is there is a compiler team underlying which will optimize it for you. Did I answer your question?
yes, sir. Yes, sir. Definitely. Thank you.
I just want to add one point to Sushim's answer. The halide is called as language. It's actually an abstraction of C++, a little bit higher than C++, because you can compile, or you should compile the halide code with C++ compiler. It's just that the extra classes that are defined that will make this appear like a new programming language, but it's not really actually a new programming language. It's just high level of abstraction of some C++ stuff. So so if someone is familiar with C++, it's very easy for them to understand halide, and it's much more easier for them to code in halide without worrying about a lot of details. And since halide is actually much higher level, so it's easier for you to specify the directives kind of things that you're talking about, that Xilinx has much more easily here. And the other advantage is the portability. Like if you have written something in halide, it doesn't matter like whether you're compiling for Hexagon, that's Qualcomm's processor, or some other architecture. Like it's if you have your custom directives, then you will lose portability. So halide will provide the benefit of portability as well as the abstraction that will help the compiler in deciding better optimizations.
Yeah. As I said in my presentation earlier, halide and TVM adoption is like growing like anything. So having a custom language within the company versus something which is portable across makes a lot of sense.
Okay, so sir, I just have another thing. So like, suppose I have a different architecture for some entirely different purpose, not image processing. suppose like some cryptographic tools or something like that. So like, and if I want to like deploy some cryptographic algorithm on that particular piece of hardware, so can we use the halide for
Okay.
that also, or like it's like only for the
So answer is not very simple. So because earlier I would have been said no, but I had to chew my words long back. We were again the same roadshow in a conference where we were talking about halide, and people asked me, is halide is right language for doing machine learning? And I was under the opinion, or a very strong opinion, that it's a domain specific language, is done for image processing. You should not do image processing, machine learning using halide. So I said word no. But then later I saw people used halide to implement lot of machine learning ops. Not us, not only later, multiple companies, multiple open source players, uh, multiple programmers. I saw from so many sources that people used halide for machine learning. So it was not designed for machine learning, and they used it for machine learning. uh, I us as a Qualcomm, we would have not explored for this use case. Uh, but theoretically, it may be possible, or it may not possible. Somebody will have to try and do it. Yeah. So yeah, answer is yes and no both. Somebody will have to try and do it. I will not give answer like 4 years back when I said no, you cannot do machine learning in halide, and then people did it. So it's a hazy answer, but that's the answer, Garvit.
Yes, sir. Okay.
Any other questions? I think we have finished the questions, right? Any more? We are here. I and Ravi will answer till the time the questions exhaust. If there are no more questions, then we can
Hello.
agree. Yeah, go ahead.
So this is like not part of the session, but like just asking, as you said that you were like looking to double your team. So I was just wondering, like on and let's say an average day, what is your team doing that like requires so many people? Like for example, are you guys like pushing to LLVM or like?
Okay.
I was just asking.
Okay. So what happens is, like, compiler team are generally very, very minuscule in every company in the size of the overall company. And they remained at that size for very, very long time. So this work is growing because of explosion in underlying architectures. It is not that it is a repetitive manual work we'll be doing. We'll be understanding a new architecture and writing optimizations for that architecture. Sometimes we'll have a new version of our one of micro controllers coming in, and it required some optimizations. Recently the work was presented at CGO, where we did some optimization to get a double digit performance improvement. So more or less, if I summarize, our work will be around doing more compiler optimizations and more security and hygiene scenarios. It will not be a repetitive manual work where we are just porting another optimization to another framework, or just that one. So the explosion is due to there are more and more underlying underlying hardware architecture. So we have to write more and more optimizations. And earlier there was one halide domain specific language we were supporting. Now there comes a TVM which you write Python, which is known to be highly unoptimized for a embedded hardware below. So optimizing them will take a lot of work. And again, security is very, very important. So it takes a lot of work out there too. For example, I'll give you one more simple example which recently has happened. x86 were power hungry as compared to ARM. as in public domain. So the laptops now, or with the 5G data rates coming in the picture and 4G data rates coming in the picture, a lot of in the developed world and a lot of countries, people are using laptops with the same. So your laptop is becoming more and more mobile, and it is carried everywhere. It is always connected. So ARM-based a lot of laptops came in the picture, which were consuming lesser power. But evolution of the whole ecosystem of developers and programmers, Windows is highly optimized for over the time on x86 uh, architecture, but not yet a lot of apps and programs are optimized for if ARM is the underlying architecture. So there is a lot of work in compiler going on so that those written apps or programs or OS need not be changed to become more efficient or faster on underlying architecture. So this is another example. So with lot of this IoT explosion, now if you see everything has a computer. In auto, like roughly more than 10 chips, you would have read about the auto production line stopping because of no chip, because of the chip supply was a problem. So that is the primary reason for explosion of compiler steam. Ravi, correct me if I'm right, or if you want to add anything here.
Yeah, that's right, Sushim. Yeah. So mainly the requirement comes from the um, fact that like we have new hardware architecture accelerators to support for specific application, like Sushim mentioned, like for image processing, dedicated hardware for image processing or machine learning applications, and that would need new compilers. And also even otherwise there is a realization that like the existing hardware is can be used more efficiently if you have better compilers than always going for like uh, improving the hardware. So you write better software, or you write better compilers to optimize your code, then you can use the existing hardware um, uh, um, uh, probably more completely and more efficiently than investing in the additional hardware. I mean, this becomes pretty important when you have the devices that we're having now, like for example, the IoT kind of devices with small form factor, where you cannot keep on increasing, like for example, memory or processor performance, because they come with different kinds of constraints. So that's another reason why we need to have like efficient software running on them, like, without increasing the hardware budget.
Yeah. Just to add to Ravi, like for example, this constrained IoT case he has talked about. We had one scenario like this high-end smartphones you see nowadays, 8 GB, 16 GB, and all those kind of memories. And there was a case where we were talking about KBs and MBs. And these high-end devices, let's say one of our optimization is saving a couple of MBs. People are not much excited about it. And on the IoT device, we asked, how much memory you save, which will make you excited. They said even 5 KB is great. So they are so constrained devices also available. So optimizations are in both directions, performance and memory. They are highly required, and more we optimize, more it is better. And as we said, that Moore's law is slowing down. So hardware is not or will not be evolving as fast as it was. So in that anticipation, also compiler becomes very, very important. Very long answer, but I hope we have answered your question.
Okay, that helps, but like that leads me to another question now. Like as you said about memory, so in my experience, a lot of optimizations trade off, let's say, memory for execution speed. So like they would
Yes.
be fatter but run faster. So
Yes.
how is this trade-off managed, like generally speaking?
So yes, there is a trade-off, and then comes the point like what will be the right point of performance and memory which this device can take. Then what happens is it pushes us also. For example, we had a memory optimization which had performance penalty. So we worked that on continuously a thin version of it, and we came up with a version where performance penalty was almost negligible. So there is a trade-off which we decide depending on, you know, what hardware we are targeting it for, where it is memory is more important or performance is more important. So there is definitely a trade-off, and at that time, your system design engineers, which is you, takes the decision in favor of one of those two things. Yes, there is a trade-off.
All right, thank you.
Any more questions? Yeah, if there are no more questions, we can probably stop the recording.